ecosystem functions, how the human civilization is getting benefit from these ecosystem services, those things need to be valued. Okay, now there are other aspects also that the problem that comes into the picture is that nature itself has no market. What does it mean, nature has no market? Nature has no market because the reason is that there is no ownership right, there is no private property right of nature. And as there is no private property right of nature, therefore neither it can be sold nor it can be purchased. Who will purchase? Who will sell? There is no one. There is no one who can sell the solar light. There is no one who can sell the air. Okay, so that's how it works, and it creates a problem because in case of privately owned commodities, there are ownership rights, clearly defined property rights, and somebody can sell and somebody else can purchase. Okay, so in general cases, the market-based goods can be sold out, can be purchased by the people, and price can be a signal of a scarcity of a particular resource or a particular commodity, which is not possible in case of nature. That's what I'm saying. Now, here there are different types of methods which are used in case of capturing the values of natural resources, which can never be traded in the way the other commodities or normal goods are traded. Okay. Here comes a very important role of the combinations of the variables which are interlinked to each other. Okay, so this is a kind of combination which is complex in nature. And from there, the importance of tools like regressions comes into the picture. Okay, so today's topic, we are just going to discuss about the very basics of a regression equation, and at the end we will see that how statistical software like SPSS can be used just to ease out your difficulties about the calculations, so that you can just by clicking your mouse couple of times you can get a result. Most important thing is that after using that, after getting the result, whatever result is coming out, you have to interpret. Your SPSS is not going to interpret that. It will only calculate. It will only give you some numbers, and you have to understand the complexities of the entire process so that you can correctly find out the results and interpret the results properly. Okay, let us see whether we can see something or not. Is it visible? Is it visible?
Sir, slide is not visible yet.
Slide is not visible.
Yes.
Okay. Let me try. If I click on this, if I do share, then now is it visible?
Yes,
Yes,
yes.
sir. Yes, sir.
Now
You
we
can
can.
say yes.
Okay. So we are just trying to plan to understand the basics of a regression and then using SPSS, where I thought initially that it should always be better if we try to understand the very basics of a regression model, because what we do in theories also. Theory is nothing but the kind of relationship the complex variables are having to minimize the complexities and to understand the basic relationship between the variables or among the variables in any case. Okay, and we are having lots of assumptions for that. Now these assumptions are to create a framework. Now, within that framework, what kind of relationship is existing between or among the variables, that creates a theory. Okay, and over time, if you relax the assumptions one by one, your theory may enrich itself. Okay, so how this is how it works actually. Now in regression also, if you think about the real life situations, the real life situations is always complex. But if you see that yes, I really want to know what kind of relationship is existing in a framework, then we have to make it as simple as possible. Okay, then gradually we can relax the assumptions and can our theory can come very close to the real life situations or complex situations. I mean the way we have our education from school life to college life to university life. Initially we starts with addition, multiplications, etc. And at class 11, 12, we do this differentiation, integrations, and all these things. Okay, so easiest one to the toughest one, if I say in that way. Uh, let me put it in a very easy way. What is regression? See, the real life situation involves complex relationship between or among variables. Variables means whatever we do, we can interpret it in some way or other, the relationships between or among variables. You go to the market, you have a wallet in your pocket, and you want to purchase something. Okay, so why you want to purchase something? Because you want to sustain your and your family's life. In that situation, there are certain variables. One is your level of satisfaction, and that level of satisfaction will highly be infected or affected rather by the price of the commodities you want to purchase, the taste and preference that you have, and the amount of money that you are having in your wallet. Okay, so three variables or four variables are there. These three, four variables are related to each other, and finally, they will affect your level of satisfaction. Okay, so there are variables in our daily life also. We may see sometimes if we want to see, we can find out the variables there. If we do not want to see, just let it be. But they are there. They are lying there. If we have the mind to see, then we can see them. The researcher in social science need to address these complex relationships using structured models, using different structured models. So there are a lot of models there, but we will start from a very basic one. Now, it is not only the degree of association between or among the variable which is important. We may want to know that, okay, fine, there are two variables, whether they are related or not. If that is the situation, that is what the researcher want to know, then that can easily be handled with the other tools like a correlation, that whether these two variables are related or not, that can be done with the help of correlation. But sometimes this attachment is not exactly what a researcher want to know. Maybe the researcher want to know about the cause-effect relationship. So if there is a cause-effect relationship, then the relationship does matter for policy purposes. Now, if the policymakers want to know that, okay, fine, I need to do something for this society. Now, if I need to do something for the society, the first thing I have to know is the status of the society. Now, the status of the society means the status of the people who are living there in the society. Okay, so the people actually, the set of people actually consists the society. So if you think about the society, you have to think about the people. If you have to think about the people, then you have to think about the relationships prevailing within this set of people. Okay. Now let me put it in this way, that whenever we are focusing on a problem, the problem has no particular fraternity. We the people belonging from different backgrounds, we have our own nature of looking into the problem from our own, you know, beneficial angle or own angle, from where we are actually, we have educated ourselves. Like if I am a student of economics, then I will look into a problem from an economic angle. If somebody is from sociology, then he or she will be looking into the problem from social angle. If somebody is from political science, then he or she will be looking into that particular problem, the same problem, from a political angle. But unless and until from all the angles the problem, the solution comes into the picture, the entire problem in totality can never be solved. Okay, so that's why nowadays the peripheral research are coming on in a big way. That in one particular sector, one particular fraternity, one particular faculty, or one particular subject, the core research is, going down, and collaborative research is coming in a big way, because we are really trying to attack a problem, trying to find out a solution of the problem from different angles, so that the problem goes forever. Okay. Now, here in this particular case, if we think about the complex relationship between or among variables, we have one statistical tool which is known as a regression, and regression comes under a framework with certain assumptions. As I said, that we are trying to make these things simple, the very basics. So we need assumptions. We are making framework, and within the framework, we are trying to understand what kind of relationship is existing between or among the variables we are trying to consider. Now, the simplest regression model is known as a simple linear regression model or classical linear regression model. Very basic, very basic. Now, obviously, if we need to apply a model, what is the most important thing that we need? We need data. We need information. Without information, nothing is possible. Okay, so the kind of data that we can use in any kind of a regression model, there are a lot of regression models. We have vast literature on regression, regression equations, types of regressions, linear regressions, non-linear regressions, parametric, non-parametric, etc., etc., etc. Three types of data. Nowadays, the fourth type has come, are there. One is a time series data, one is a cross-section data, the third one is a pooled data, and fourth one is a panel data. Time series data, we all know that it's a set of observations on the values that a variable takes at different times or different point of times. Such data may be collected at regular time interval. It may be the daily basis data, it may be weekly data, it may be a yearly data, it can be a monthly data, depending on the type of variable you are considering, depending on the type of research the researcher is interested about. If you think about a cross-section data, then cross-section data are data on one or more variables collected at the same point of time. Maybe some researcher is interested about, comparing the states, major states of the country in terms of agricultural crop production. Which state has produced more, which state has produced less in a particular point of time, maybe for a particular year, 2019 to 2020. Okay, in that case, at the same point of time, the data on agricultural crops produced has been collected from 14 major states of the country, and in that way they have the researcher will be able to understand that, okay, fine, this has efficiently produced and that particular state has not in that way efficiently produced the agricultural crops. Now, in some times, this time series data and cross-section data for some research purpose may not be sufficient enough for statistical tools or statistical explanation. So in that case, there is the third type of data that can be used is known as a pooled data. Now, pooled data are containing elements of both time series and cross-section data. You may have, the researcher may have a very small time series data. Even the researcher may have a very small cross-section data. So the time series data and cross-section data individually are very small in size and cannot be applicable or cannot be used in case of any kind of statistical measure. So in that case, if the time series and cross-section data can be pulled together, then the data set will be large enough, then a statistical analysis, particularly a regression analysis, can be done. The fourth type of data, which is nowadays is famous, is known as the panel data, where a special type of pool data in which the same cross-sectional unit is surveyed over time. So one particular cross-sectional unit may be a set of households, maybe a set of farms. The data is being collected over time again and again and again and again. And in that case, the data set that has been prepared is known as a panel data. Now, in case of regression, we know that the easiest one is a uh, binary regression model, that there will be one particular dependent variable and there will be one independent variable. But in our case, let us talk about the multiple regression model, where there is at least two independent variable or more independent variable and one dependent variable. So simply, in case of multiple linear regression, it is a method for studying the relationship between a dependent variable and two or more independent variables. So ideally, what we want to do, we are trying to understand the relationship between the dependent variable and the set of independent variables that we are having. What is the purpose of a multiple linear regression model? We need to predict about the future. We are trying to explain the relationship that is existing there between the set of variables predicted, I mean the dependent variable and the set of independent variable, and in some way we are trying to establish a theory, or we are trying to build a theory that okay, if this is the situation under certain framework, under certain assumptions, if this is the kind of relationship existing among these variables, then that can talk about or think about a particular theory. So the purpose of a multiple linear regression is basically prediction, explanation, and theory building. Now, how to conduct an operation? I put it in this way, that how to conduct an operation, that means how to do a regression, multiple linear regression. MLR produces a model that identifies the best weighted combination of independent variables to predict the dependent or criteria variable. So in a left-hand side of an equation, we have one particular variable which is known as a dependent variable or a predict variable, criteria variable, and on the right side of the equation, we have two or more independent variable who is supposed to affect the dependent variable. So we are trying to understand the relationship existing among the independent set of variables and the dependent variable. See, here we have written y predicted variable, equal to a plus b1 x1 plus b2 x2 plus dot 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 plus bn xn. So we have n number of variables. As I said, that life is complex in nature. And as life is complex in nature, then there are large number of variables we are actually dealing in our daily life situation. So in a real life situation, you are actually dealing with number of variables, and we have taken that, okay, fine, there are n number of variables. So our job is to know that how this a plus b1 x1 plus b2 x2 plus dot 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 plus bn xn, these number of independent variables, how they are affecting this predictive variable or the kind of dependent variable. See, the MLR estimates the relative importance of several hypothesized predictors. These are the predictors. X1, X2, Xn, these are the predictors. So how X1 is affecting the Y, how X2 is affecting the Y, how Xn is affecting the Y, how maybe Xi is affecting the Y. That is the job of multiple linear regression model. MLR assess the contribution of the combined variables to change the dependent variable. That means when we are talking about the predictions, then the entire impact of these set of independent variables, how it is impacting the Y, the dependent variable for prediction, that also multiple linear regression performs. Okay. Now there is a design requirement for the multiple linear regression. What is that? There will be one dependent variable. You cannot handle two dependent variable and multiple independent variables. That is not possible. Okay. Now, two or more independent variables in case of a multiple linear regression model is required. Predictor or explanatory variables. The independent variable is also known as a predictor variable, also known as the explanatory variables. In general, sample size, though we in statistics there is a rule of thumb that if you take 30 samples, 30 or more than 30 samples, then that is a large sample. If you take less than 30 samples, then that is a small sample. Here we are telling that okay, it's greater than equal to 50. That means at least 10 times as many cases as independent variables. So you cannot take the sample size lower than the number of variables, number of independent variables you are having, because that is not going to give you a result. There should be sufficient amount of samples compared to the number of independent variables. So these are the design requirements for very basic design requirements for a multiple linear regression model. Now, this slide talks about the variations in the model. Variation means let's go back to the earlier one. Okay. Here I said that this Y predictable or the dependent variable will be impacted by these independent variables. Now the way it impacts is x1, x2, x3, x4, xn. These are the variables that can take any value. Okay. Now, if this variable is taking a large number of values, this variable is also taking a large number of values, this variable is also taking a large number of values, then there will be heterogeneity in the number of responses that each of the variable is having. Similarly, this predicted variable is also having some kind of value. Now, in that case, this multiple linear regression model actually measures the variation in the dependent variable due to the variation of this independent variable. Variation in this dependent variable due to the variation of this independent variable. Similarly, the variation in this dependent variable due to the variation in this independent variable. That means here in this case, variations in the model tells that total variation is this entire thing, entire larger circuit. Total variation in Y, that means total variation in the dependent variable. Now this total variation can have two parts. One is variation in the predicted variables or the independent variables, and there may be some variations which can occur due to some other reasons. Let me put it in this way, that we have a regression model where this is the amount of output purchased in the market. Now this amount of output may depend on the price of the commodity that you are purchasing. Maybe this X1 is the price of that commodity. Maybe this is a taste and preference that the individual who is purchasing is having. Maybe there is another variable which is income of the individual. Okay, now if we have considered only price and income, and we are not considering something which is like taste and preferences, like family size and others, like the price of a related commodity, then that can be considered as a error term, uncorrelated error term. So in the model, this variation is due to the variation in x1s, in x2s, in x3s and x4s, which the researcher has written in the model. Now, apart from that, maybe the researcher has not incorporated some other variable which also has an impact on the dependent variable. This part, yellowish part, is that particular unpredictable variation part where the researcher may have or could have incorporated the variables but have not incorporated the variables. So that is in the uncorrelated error term. That means the variables which could have been considered but has not been considered in the model, because you are trying to make the model a little simpler one. Okay, so total variation in the dependent variable can be due to the variation by the independent variable you have a researcher have predicted in the model, or other than that, there can be variations which could have been made by the variables which has not been incorporated in the model. Okay. Now, the basic assumptions of a multiple linear regression model is that it should be independent. The data of any particular subject are independent of the data of all other subjects. That means the data on X1 is not going to impact on the data of X2, X3 or Xn. Data of X2 must not have an impact on X1, X3, X4 or Xn. Data on Xn must not have impact on the earlier data sets. Okay, so the data will be independent. There will be a normality in the population. The data on the dependent variable are normally distributed for each of the possible combinations of the level of the X variables. Each of the variable is normally distributed. Now, normally distributed means, do we have any idea about normality? Can we discuss? Please feel free. It's a discussion, nothing else. You see, in statistics, there will be always the condition of normality will be there. Anyone, please feel free. Yeah, hello.
মাসিকে আজকে আমি একটা হলমারি কিনবো।
Can we have any discussion on normality? Let us see. Let us just see.
Hello, Samrat sir.
Yes, sir. Yes, sir.
This is Ratan.
Okay, sir. How are you?
Fine. So, see, from science background, we use Origin software.
Okay.
So, how it is different from that SPSS?
Actually, SPSS is completely, Windows based in the sense, it's completely user friendly. Okay, you don't need to put any code, you don't need to write any code. Whatever you have, you can see on the screen, and you can easily operate that. Okay, you have seen R also. I think you have also seen R software. The problem that sometimes people may feel is like R is fantastic. I don't say that R is not not fantastic. R is fantastic, but the problem is that SPSS you can learn by yourself, but for R you need some guidance because it is requiring some kind of write up. The writing is required. Okay, the programs are required, but SPSS is window based, so you can easily find out from the like the taskbar that you can find out that okay, fine, there is a data analysis, so you go to the data analysis, you can go for regression, then you go to linear regression, you can find out the dialog box for that, and you can use that also. Okay, so that is basically the good thing for SPSS. The problem of SPSS is that it is a registered software that requires to purchase. Okay, for R,
Yes,
you
yes,
don't
yes,
need
yes.
to purchase. It's a free software, so whoever want can download and can use that. But SPSS, either institutionally or personally, you need to purchase. So that's a big problem, and it's costly.
Oh,
Hmm.
okay, sir.
Because nowadays what is happening is that uh, Web of Science or Scopus, the category 1 journals, they also require the identification key also. Okay, so if you have done anything using SPSS, what you have to do, you have to provide the key also, that password. Okay,
Yes, yes, yes,
and they
yes,
will
yes.
verify that. Because
Oh,
in particularly in many countries, many of the researchers, they have no other option but using a kind of version which is not authenticated. That's a big problem. Okay.
oh. So may I know, sir, kindly, can you tell me the price of that software, which is around?
Right now I cannot tell, but it was more than a lakh.
Oh my God.
So it's not possible for individual purchase. Okay, but
Okay,
the
okay.
institutions, most of the institutions, they are having that is usable. I
Uh,
mean, for 3 users or 5 users, they used to provide. So that is even our university is also having, I think, because economics department was
wow.
having one. 5 users support was there, I think.
Or
Hmm.
library has or what?
Library may be having one. Library may be having one.
Okay,
That is
okay,
that is
okay.
that is available in our university. Hmm.
Oh, thank you. Thank you very
Thank
much, sir.
thank you, sir. Thank you so much. Anyone, can we have any comment on this normality, data normality, because that is very important.
Sir, in my opinion, normality means the deviation in the sample sizes. If the sample sizes are very close to means, that means the normality is high, and if the
Mhm.
sample size is very much deviated from the mean, the normality is low.
Okay, that means if we put it in this way, that can we go back a little, talking about mean and standard deviation? That will be better to understand. If we see that we take just randomly two numbers, 45 and 55. Okay, we have two values, 45 and 55, and the mean of these two is 50. Okay, but if you see that 45 is very close to 50 and 55 is also very close to 50. 5 points on the left and 5 points on the right if we consider the mean as 50. This is one particular data set. Second particular data set, if we consider that the mean between 5 and 95, then that is also 50. Now, if we compare these two data sets, one is 5 and 95, the other one is 45 and 55. See the stretch of the data. 45 and 55 is very close to 50, as you said, that
Yes.
they are very close to 50. 5 and 95 is very far from 50. But if you consider only the mean value, then we cannot understand properly the spread of the data set, how spread it is.
Yes.
We all know that this normal distribution, it looks like a bell-shaped distribution, absolutely symmetric in nature. Like if you fold this normally distributed data set, then it will superimpose on either of the sides. Okay. Now the tendency is that if most of the data are closer towards the mean value, then automatically the mean, median, and mode will superimpose in one particular value. And we have, the outliers. That means the last values on either of the sides will be very less in number. That's why it looks like a bell-shaped distribution. Okay, it's like a bell. So Generally, we consider that we have a normally distributed population, because unless and until we have a normally distributed populations, the general statistical framework is not usable in our research. Okay. Now the third point, third basic assumption is talking about a homoscedasticity, where in the population, the variances of the dependent variable for each of the possible combinations of the level of the x variables are equal. Homoscedastic in nature. Variances of the dependent variable for each of the possible combinations of the level of the x variables are equal. That means they are having a homoscedastic type of distribution in nature about the, about the variables. Now the fourth point is linearity. It tells that in the population, the relation between the dependent variable and the independent variable is linear when all other independent variables are held constant. So there is a relationship, a one-to-one relationship, which is a linear relationship existing between the dependent and independent variable. On the other hand, it may so happen that even the parameters are also linearly related. That's why we have seen that in the population, this term is there in the population. The parameters can be linearly related. The variables can also be linearly related. Okay, so in that way, the multiple linear regression name comes into the picture. Multiple number of regression, number of variables are there, large number of variables are there, and they are linearly related to each other. Now, what is the difference between simple regression versus multiple regression? Simple regression and multiple regression. See, one dependent variable y predicted from one independent variable x in case of simple linear regression. In case of multiple linear regression, as I said, as we all know, that one dependent variable y is predicted from set of independent variables like x1, x2, up to xk or xn, whatever it may be. So we have in simple regression one regression coefficient, in multiple regression one regression coefficient for each of the independent variable. That means that b1 is a particular regression coefficient. B2 is another regression coefficient for x2. B3 is another regression coefficient for x3. Because our purpose of multiple linear regression was to understand the impact of x1 on y, impact of x2 on y, impact of x3 on y, and so on. And in that way, this B1, which is the coefficient of x1, is going to tell you how it is impacting the predicted variable. There is a R-square, which is a proportion of variation in the dependent variable y, predictable from x. That means the proportion of variation in the dependent variable predictable from the independent variable. There is a large, capital R-square, sorry, in case of multiple regression, where the proportion of variation in dependent variable y predictable by a set of independent variables, x's, x1, x2, x3, x4. If there are 17 variables, then x1 to x17. Altogether, how they can impact, they are impacting this predicted variable or the dependent variable, that is measured with the help of this capital R square. Let's see what is the next thing. Yeah, we have a multiple linear regression equation where we are actually having y predicted value equal to, this is a constant value, a is a constant, plus b1 is a coefficient of x1, plus b2 is a coefficient of x2, plus so on, bn is a coefficient of xn. Pred is a predicted, 1 and 2 are the underscores that we are having. See, y pred, dependent variable or the variable to be predicted, x, any of the x, xi you can say, the independent or predictor variables. A is the raw score equations, include a constant or y, that is the intercept of y-axis representing the value of y when x equal to 0. I can tell you one particular example here, just for this A. It tells that very simple way to understand is that something, when we go to the market to purchase, let's say, the absolute necessities like rice, like our staple food. If the price varies very highly, can we not, should we not purchase at all that particular commodity which is absolutely essential for us? We will purchase. If I am a fond of a rice, I don't have any other option but purchasing rice. Maybe the price of rice has increased by 10 rupees, but I will purchase some amount of rice. Okay, so this price, maybe this is the price of the commodity. This is not going to affect this particular variable, a particular constant, I mean the term constant. Okay, maybe I'm not having a job. That means if x1 is my income, this is 0. Let's say we have only these two, a plus b1 x1. I have no income. If this is 0, then b1 x1 is also 0. But in that case also, my quantity purchase will be of this amount, because maybe I am having some amount of money which I have saved when I was working. So I'm spending that for sustaining my family and my livelihood. Okay, so in that way, this is basically the intercept term on the y-axis. See, intercept term on the y-axis representing the value of y when x equal to 0. So y will be having that value. If all the x's will be 0, y will be having that value of this a. So in the multiple linear regression equation, when we put all the data, this a will be having a value also. Okay, b is a weight or partial regression coefficients. Now these b's show the relative contribution of their independent variable on the dependent variable when controlling for other effect of controlling for the effects of the other predictors. So one by one we will see that this b1 will give the impact of x1 on y, keeping these others constant. When we consider b2, this b2, the value in terms of a numerical figure, that will give the contribution of this x2 on y, keeping the others constant. Similarly, this bn is going to give you the idea about the contribution of this xn on y, keeping the others constant, rest of them constant. So this is how the multiple linear regression equation looks like. Now, what are the variables in the model? Let's say there are two approaches. One approach is to perform literature review and examine theories to identify the potential predictors, thus building a theoretical variate which may reflect the particular relevance of the variable. Maybe this is on the basis of the literature review, that okay, fine, I know the theory was there, so I try to understand what exact kind of relationship is existing and what I am trying to find out on the basis of the platform of the past studies, past literature, that okay, fine, this type of regression equations have already been seen, have already been studied by the researchers. So on the basis of that, I try to develop my knowledge. I try to develop my concept. I try to find out the set of variables I should consider in my case. Okay, so this is one particular type of model building. This is sometimes referred to as the standard simultaneous regression method. A second type of method is there, the second approach, that is to examine the statistics that shows the effect of each variable both within and out of the equation. So individual variables x1, x2, x3, xn, how they are predicting the y, and altogether the set of variables, how the set is affecting the y. These two are the ways to see the relationship. Now there is an output. Obviously, if we run a regression, then definitely we will be having an output. How it looks like? The following notions are essential for understanding the MLR output: R square, adjusted R square, constant, beta coefficients or B, beta, then there will be a F test, and then there will be a T test. So these are the things that will come out whenever we we perform a regression equation. So these things will tell us whether the kind of model we have used, we have conceptualized, we have framed, whether they will be acceptable or not acceptable. For multiple linear regression, R square, this is a mistake. That is, this will be R square, adjusted R square. Okay, mistakenly this has been R2. For MLR, R square, the coefficient of multiple determination is used rather than small r, that is Pearson's correlation coefficient, to assess the strength of this more complex relationship as compared to a bivariate correlation. So in correlation, what we see, we try to understand the kind of association is, existing, whether there is association or not. If they are not associated, R will be having 0. If they are associated, then either it will be very close or pointing towards positive +1 or towards -1. If they are, directly related, then the R value, the small r value, will be directing towards +1, +1. If they are negatively related, adversely related, then they will be moved towards -1. Okay, so that's how this Pearson correlation coefficient is actually working. But in case of regression, this R square is actually giving you some value to understand whether the model you have created is acceptable to you or it is not acceptable to you. Whether the variables you have considered for creating a model, whether those variables are the proper variables or are not that proper in nature. We can understand using these outputs: R square, adjusted R square, constant, B coefficient, beta, F test, and T test. Sorry. Now let us see adjusted R square and B coefficients. The adjusted R square adjusts for the inflation caused by the number of variables in the equation. As the sample size increases, adjustment is less needed. That means you don't need to adjust R square. Automatically it will come. You will see there are two values. One is R square, the other one is adjusted R square. Now R square value is little inflated in nature, and it is basically influenced by the sample size. If you increase the sample size, then automatically the value of R square will also increase. But that will be, kept a little more proper, in a little more proper way, if you use adjusted R square instead of R square. On the other hand, and this is this R square or adjusted R square, this is basically for the entire model. Now, the second one, that is the B coefficient, it measures the amount of increase or decrease in the dependent variable for a 1 unit difference in the independent variable. That means if we increase the value of x1 by 1 unit, we can see that how the y changes, and that is visible with the help of the value of b that we are having. For x1, we have to see b1. That b1 will tell what will happen, what exactly is happening. Independent variable controlling for the other independent variables in the equation. That means once we are talking about x1, we will be interested about b1 only. We are not interested about the others. When we are talking about x2, then we are interested about b2 only, not about the others, x1 or b1 or b3, b4 and bn and all. Okay, so this is how it works. Ideally, the independent variables are uncorrelated. What does this mean? Uncorrelated means, that means we have taken the values of x1, x2, x3 separately, and the researcher will always want that these values of x1 should have no relation with the values of x2, or should have no relation with the values of x3 and so on. So ideally they will be uncorrelated. x1 has no impact on x2, x2 has no impact on x3, x3 has no impact on x4, or x1 has no impact on x3. In this way, they will be considered as uncorrelated. If there is a correlation, if the x1, the values of x1 is going to impact the value of x2, then definitely the value of b1 and the value of b2, these two will also be interrelated to each other. What will happen? The way, the amount of or the proportion of influence that x1 was having on y and the x2 was having on y separately, these two value will not be the accurate value. So for accuracy, we need to have independent variables to be uncorrelated in terms of their responses, in terms of their quantitative values. Consequently, controlling for one of them will not affect the relationship between the other independent variable and the dependent variable. So if you want to control, if you want to change, if you want to control one particular variable, then if two variables are not correlated, then the others will not be impacted. If you want to control the x2 variable, and if x2 and x1 are not correlated, then the change in the x2 variable will not have any impact on the values of the x1 variable. So that's how they are uncorrelated, and they should be uncorrelated for an ideal multiple linear regression equation model in that way. Now, intercorrelations or collinearity, it tells that if the two independent variables are uncorrelated, we can uniquely partition the amount of variance in y due to x1 and x2, and bias can be avoided. As I said earlier, just said that if x1 and x2, these two are not correlated to each other, then prediction of change in y, variance in y, due to x1 and predictions in variance in y due to x2 can better be explained. Okay, so for that explanation, uncorrelation is very important between or among the independent variables. Now, small intercorrelations between the independent variables will not greatly bias the B coefficient. So if there is a very small intercorrelation, that may be avoided. But if there are huge intercorrelation between x1 and x2, maybe the values of x1 that we are having, that is the square of the values of x2 that we are having, then it will be highly undesirable. That kind of x1 and x2 correlation is highly undesirable, because then b1 for x1 and b2 for x2 will be highly correlated to each other. So that means the variance in y due to x1 and the variance in y due to x2 cannot be independently explained in that way through that particular model. Okay. Now, in case of multiple linear regression model building, each predictor is taken in turn. That is, all other predictors are first placed in the equation, and then the predictors of interest is entered. That means how you will think about the model, how you will predict the model, how you will structure the model. Y equal to which one will be x1, which one will be x2, which one will be x3. It tells that you have a background study, maybe, as I have said earlier also in the earlier slides, also some of the slides. Yeah, literature review. If the researcher have done a proper literature review, then definitely he or she will be having an idea about the importance of the variables. Now, if the importance of the variable is clear to the researcher, the conceptual clarity is there to the researcher, then definitely the most important variable will be considered as x1. The second most important will be considered as x2, and so on. Okay, so this allows us to determine the unique additional contribution of the predictor variable. By repeating the procedure for each predictor, we can determine the unique contribution of each of the independent variables in the model. There are different ways of building a regression model. Like, we have a simultaneous system for this. All independent variables entered together. It can be stepwise, that means independent variables entered according to some order, like by size or correlation with dependent variable. Maybe x1 is having a highest correlation with y, so the particular variable which is having highest correlation with y is considered as x1. The next highest correlation, next best correlation with y will be considered as x2. The third next best correlation with y will be considered as x3, and so on, or in order of significance. So due to literature review, the researcher knows that, okay, this is generally in the past studies has given an idea that, okay, these are the variables which are most important. So the most important variable will be considered as x1, then x2, then x3, and so on. And there is another way, that is hierarchical. That means independent variables entered in stages, step by step, stage by stage. Okay, the most important variable comes. So we have one particular multiple linear regression model. Then you have added another variable. So you have another second multiple linear regression model. Then another third variable comes into the picture. So you have third multiple linear regression model. So in this way, you are developing your model in a hierarchical manner. Now, there are various significance tests are there. One is testing R-square. Tests R-square through F-test. Test of competing models, like differences between R-squares. You have two models. Each of them are having R-square values. So in terms of R-square values, you can say that, okay, model 1 is better than model 2, or model 2 is better than model 1, in that way, through an F-test or differences of R-square. Testing B, that means the individual coefficients. Test of each partial regression coefficient by t-test. Comparison of partial regression coefficients with each other. T-test of difference between standardized partial regression coefficients. So you can compare them also, B values. Particularly in case of F and t-test, t-tests are used to test the significance of each predictor in the equation. That is the t-values. In terms of t-values, you can see whether the predictor is significant in the equation or not. Particular x value is the particular variable is significant or not. You can understand using the values of t, just seeing the values of t. The null hypothesis is that predictor's weight is effectively equal to 0 when the effects of the other predictors are taken into account. Okay, so this is basically the null hypothesis. The name itself is telling. Hence, it does not contribute to the variance in the dependent variable within the population. So that is the importance of F-test and t-test. What about the R-square? When comparing the R-square of an original set of variables to the R-square after additional variables have been included, the researcher is able to identify the unique variation explained by the additional set of variables. So you have one model particularly that is having one set of one particular value of R-square. Now you have added some other variables. We thought that, okay, fine, that is also important. So we should incorporate those variables in the model. So you have a second model and you have a different R-square. Then you can understand that, okay, fine, one particular variable I have added in the second, I have added, and that has become a second model. Due to that particular variable, my model now is giving me a better result than the earlier model. Now, any covariation between the original set of variables and the new variables will be attributed to the original variables. That is also possible from this R-square. R-square, which is a multiple correlation squared, is a variation in y accounted for by the set of predictors. That means R-square tells that how much variation in the dependent variable is explained by the variation in the independent variables. So if we have three variables, x1, x2, and x3, all these three variables, their variation, how it affects the variation in the predicted variable, that is what R-square is actually capturing. Now, adjusted R-square is a sample variation around R-square that can only lead to the inflation of the value. So as we have discussed earlier also, that if you increase the sample size, the value of R-square will also increase. So in that way, by increasing the sample size, you can inflate the value of R-square. Sometimes it was kind of idea that even in our college life also we knew, I mean university life also we knew that if we have a very good R square value, then the model is good. But that is not always true, because the value of R square can also be inflated by increasing the sample. If you have 100 samples, you have taken 100 samples and run a regression model, you get one particular R square value. If you take 200 samples, then definitely that R square value will increase. But does that mean that the relationship that was existing earlier between x1, x2, x3 and y has changed? No, that has not changed. It is only that you have taken more and more value, more and more sample. So by considering that the samples are now moving towards a population, it is increasing, by a significant amount. So the value of R square has increased. So in that sense, adjusted R square is a better measure than R square, which can be inflated by using, more by using the sample size. Let's go to a particular type of example. Let's see, we have I have considered an example which is a little from the medical fraternity. Suppose we wish to examine the factors that predict the length of hospitalization following spinal surgery in children with CP, that is dependent continuous variable. The available variables in the data set are hematocrit, estimated blood loss, cell saver, operating time, age at surgery, and parked red blood cells. These are the independent variables. Now, if the dependent and independent variables are measured on continuous scale, what will be an appropriate test statistic? Let's select appropriate variables, theory-based and statistical approach, and determine the effect of estimated blood loss while controlling hematocrit and parked red blood cell, age at surgery, cell saver operating time, duration of surgery. This is a particular table. Let me tell you that if you have data in Excel, you can export the data or import the data from Excel to SPSS. Okay, you have to go to the file, go to open dataset. Then after clicking the open dataset, then you have to write the file name. The file name will be there. If it's on desktop, then you have to go to the desktop and click on that particular Excel file. It will open. Then you have to save that, okay, with a certain name. Then this view will come. This is a data view. So we have two views. One is a data view. The other one is a variable view. If there is any any change is required, then you have to go to the variable view. If you click on the variable view will come, and you have to make the changes accordingly. See, these are the variable names. Sometimes the variable names, if you import data from Excel, sometimes the variable name will not appear. So in that case, you have to write the variable names by clicking on this variable view. The variable view window will open. Then there will be the second particular box. You can write the name of the particular variable. So this is a data view where you can see like a spreadsheet. You can see the data. Then you have to go to analyze, then go to regression, then go to the linear regression. You have to click on the linear regression. What will happen? Yeah, this will come. This will come. This is a linear regression. This is where all the variables you have considered, including the dependent variable, has been listed. So click on this dependent variable, click on this particular icon, it will be reflected here. Then consider each of the variables, independent variables, click on this particular icon, this will be considered, this will be incorporated here. Then go to the linear regression options. You have to stepping method criteria, use probability of F, where you are considering it as 5% level of significance. 5% level of significance means if you have a two-tailed problem in a normal regression, normal data set or normal data set, then you have to create a critical zone. Critical zone means 5% of standard normal variate value is creating a bar or a limit on the right side of which, if the calculated value of the variable lies, then it will be rejected. On the left side of that particular barrier, if the calculated value of the variable is lying, then it will be accepted. So it is actually this level of significance of 5%. It actually gives you an opportunity to see whether, using the data set, creating a multiple linear regression model, whether the model gives you, the opportunity to accept your null hypothesis or the opportunity to reject your null hypothesis, accept your alternative hypothesis. So this is, you have to do use probability of F. Entry value is 5% and removal is 10%, that is 0.05 to 0.10. Include constant in the equation, exclude cases listwise. Okay, then go to if you click OK, then this will come, descriptive statistics. So we have days in hospital, the mean standard deviation will be there, number of sample, this is sample size 49. Hematocrit, against that you have the mean value and standard deviation value. Estimated blood loss in CC, this is given. Pro-cop, this is another variable that is being, so all the variables, the mean and standard deviations has been given and the sample size has been given. Now this is the coefficients. This is actually the model, the output that comes into the picture, and this is the B value that we are talking about. Interpret the coefficients. These are the B values, and this is constant. This is the first variable, first independent, second independent, third independent, fourth independent, and fifth independent variables. We have 5 independent variables. These are basically this is the value of A, the equation that we are having. This is the A value of A. This is the B value, B1 value. This is B2, B3, B4, and this is B5 value. See the T values. Okay. And if you can also see the level of significance where it should be less than 10% level of significance. See, the removal is 10%. So we have to have, if we have more than 10% level of significance, then we are not going to consider the particular variable, because with more than 10% level of significance, we are actually assuming that in 90% cases it can be true. But in statistics, it's always better if you have 1% level of significance, 5% level of significance, or at most 10% level of significance. You can also see this here. None of them, they are having actually this less than 10% level of significance. Only this weight of the subject, this is having 0.023. So we can accept this. Now second part of the output, so SPSS output, it tells that the value of the R square is 0.143. What does that mean? 0.143. That means the model that we have seen here, this is y equal to A, that means y equal to minus 17.311 plus 0.558 into hematocrit plus minus 0.002 into estimated blood loss in CC plus 0.29 into PROCOB plus 0.006 into dark red blood cells in CC plus 0.416 into weight of the subject. Okay, so this is your model, and below each of these values we will write these values. So below this minus 17.311, in bracket we will write 0.8383. Under this minus 0.558, we have to write 0.203. So okay, this way. This is the way we have to write the outputs, and that will give you the regression equation. Now, for this regression equation, we can see in the earlier cases, we have seen that most of the variables are basically not significant. That means the variables the researcher has considered, they are not much important, and they are not actually individually not much contributing to explaining the variance of the dependent variable, each of them, except this weight of the subject. This is clearly can be visible from here. See, the R-square value actually gives you the validity of that particular multiple linear regression model, and the validity shows that the R-square value is only 0.143. That means in 14.3% cases, the independent variables variation is in a position to predict the dependent variables variation. I'm repeating again, in 14% cases, the variation in the independent variables variability can predict the dependent variables variability. That means in 86% cases, these variables are not in a position to predict. So the variables that the researcher has selected is not a proper set of variables to explain the dependent variable. Okay, the variables, the set of variables the researcher has been selected is not proper set of variable for explaining the variances in the predicted or dependent variable. Okay, so that's how it actually works, and this is an ANOVA where the significance is 0.230. So all of them together tells that the model is not a good fit. This is the interpretation of the R-square, and what does the ANOVA result mean? ANOVA, okay, can anyone tell me what does ANOVA means actually? Please feel free. See, variation from a particular set of data, if we talk about variation, then the variation can come from within the group, and if there are number of groups, then the variation can come from outside the groups also. Okay, so ANOVA is going to give you the idea about whether the major variation comes from within the group. If I say in a easiest way, then whether the variation is coming more from within the group or from among the group. Okay, that is the value of ANOVA tells, but the significance level is also not very encouraging here. So I'm just repeating again, this is SPSS. You have to click on SPSS, first analyze, then regression, then go to linear. After clicking, you will get this dialog box. In this dialog box, all the variables the researcher has considered has been listed here. So consider the dependent variable, click on this icon, it will be here. Consider the number of independent variables the researcher is considering. Click either one of them one by one, or select 2, 3, 4, whatever are there, and then click on this icon. All of them will be here. It's always the enter method, and then go to the statistics. You can see this will come, linear regression options will come. Use a probability of F, and entries will be from 5% to 10%. So if it is greater than 10%, then the model will not be that acceptable in nature, and exclude cases listwise. Then you go you'll get a SPSS output where the mean, standard deviation, and samples will be reflected. And this is basically the SPSS output model, the multiple linear regression model, with the values, t values and significance has been given, and then the value, the result about the particular model here, the multiple linear regression model, that will be reflected. That shows that this particular, in this case, it shows that it's very less amount of predictability this model is having, because the set of independent variables has been considered, has been used to capture it. It's very less in very inappropriate rather in nature. See the value of the adjusted R square, only 4%, 4.4%. That is not acceptable. Okay, because it's not even 10%. It is actually predicting. We have seen papers where in case of water resource management, I have seen a couple of papers where they have accepted the result when it was 47% on 42% also adjusted R square value. But here we have a value which is absolutely very less in nature. So it tells that the set of variables has been considered as independent variables. They are not properly, they are not in a position to explain the variation in the explain, I mean, the dependent variable. Okay, so it's very easy. What I will suggest is, like, if you have an access to any SPSS software, then create your own data set and just try to run the way we have done here. And now it is, you have a lot of scopes of information, but most important part is you have to understand the logic behind regression, so that the output that you have, you can interpret. Unless and until I have a clear-cut understanding, how can I understand whether the model is acceptable model or not an acceptable model? Whether the set of variables I have considered as an independent set of variables, whether they will be acceptable, they are properly explaining the the dependent variable, or they are not properly explaining the dependent variable, that is not very clear to us. Okay, so I guess I have make you bored enough and you are confused enough. Thank you so much. Thank you all.
Thank you, sir.
Thank you, Samrat Goswami sir. It's really pleasant to have you in this session. I hope our participant has got an introduction about the your SPSS programming, and